Hey there, and welcome to Into the Terminal, episode 48. Today, we're going to be talking about common disk errors you might see and how to troubleshoot them. So, we are looking at a RHEL 9.0 box out on our lab site, and at the top of the show, we wanted to talk through some helpful tools that we'll be using in the deeper dive to break some things and see if we can fix it. The funny thing is that we're actually breaking things on purpose during this episode arc. So one of the first tools that I use is df, that is disk free, that shows me all the different volumes that are currently mounted on the system. Now, I don't know about you, but looking at 1K blocks doesn't really tell me much. So what I'll do a lot of times is a df-h, that stands for human readable, and the capital P, Scott?
It formats the printing.
Oh, okay, gotcha. So yeah, df-h, capital P, helps present a very nice layout, makes it much easier to read, at least in my opinion, and as well as a percentage utilized. So that's how much free space do I have, and then so similar to that one but completely different is du, that's disk used or disk utilized. I've heard it both ways, and we can do excuse me, we can pick particular directories. Also, this is a great tool to use with some pipes and some arguments to figure out which file is the largest. So if you've got a bunch of application files and one of them is like gigabytes in size, you can use some arguments to figure out which file is the largest in that directory. Sorry, the chat is lively today. They're already trying to figure out what we're going to break and how. So I will get through these tools quickly so we can get in and break stuff. One of the next ones is lsof or lsof. I've heard it pronounced sometimes. lsof is list open files. So what this does is lets us know when a file is being called by a process. So in the days of trying to troubleshoot a broken application, I'd use lsof to figure out what files the application is still holding on to. It may have a lock on a particular file that I'm unable to read or write. So lsof allows you to figure out what files are in use and by which process. Another one that might be valuable, it's a little bit more general of a tool, is uptime, or you can get some of the same information plus a lot more using the top command. What we're looking at here is the load average, and so what that says is it's basically would be an algorithmic view of system load.
Kind of. So what the load average is telling us is the 1, 5, and 15-minute CPU run queue averages that has been run through a log function to kind of smooth out any bumps. But why this is an interesting troubleshooting tool for disk I/O is it's been in my experience that when your load average is really high, that oftentimes the reason for that is because you're having disk problems. And so what will happen is the disk is not able to resolve process requests for files, and so this processes just sit in the run queue on the CPU, which then gets factored into the load average. And so the more processes you have sitting in the run queue, the bigger and bigger and bigger your load average is. So generally, when I see out of band load averages or out of normal load averages, disk is one of the first things I check.
Logarithmic, not algorithmic. As you can tell, math was not my strong suit. So we can get a lot of the same information as well as list of running processes using the top command. You'll notice the same load average output there across the top. So you can also see the uptime. So if you're doing a little bit more deeper dive troubleshooting, top is a great command, and I believe we looked into that in one of our tool bag episodes. I'll see if I can find that and put that in the show notes. And then if we're troubleshooting disk, a great place to go is to just tail out var log messages. You can use the tail command and it'll show you the last 20 or so entries. Or if you're, it's 10. So there's There's a couple of different arguments to use here as well. You can also use the -in option to specify the number of lines that you want to show. So in this case, you can do a -in 20, and it'll show you the previous 20 lines. The one I tend to find myself using a lot is -f, which is basically -follow. So it'll actually tail out var log messages live, so you can see what's going on. This is a great way to go and say, if I click on this button in an application, the application crashes. It'll actually output the logs in real time, so you can see when you take an action what the reaction is. So tail-f, tail-in, both great tools. And then the last one I wanted to mention was dmesg. What this is basically outputs different subsystems within the operating system. You'll see kernel or systemd are outputting log messages, and of course, you see that we've got a couple of messages in red, which is bad. Scott, I think you were getting ready to say something.
Yeah, the technical term for this is the kernel message ring buffer. So dmesg shows you what's in the kernel message ring buffer. The var log dmesg file is a copy of this that's made at some point. But dmesg command shows you live what's in the kernel message ring buffer. The message ring is finite sized. So over time, old messages will scroll away and new messages always get added to the bottom.
So add that to your list of trivia, and you can stump your friends with the system ring. That's actually not something I heard. I just always called it dmesg, and I've been wrong. So those are some of the main tools: df, du, lsof, top and uptime, messages, dmesg. The chat has a few others that they're throwing around, including some additional arguments for commands. Including journal CTL is a good one to add. But I think that's kind of a good overview of the tools that we're going to look into today. So now's the time in the show to definitely get to join us live. We'll be transitioning to the second half of the show. We'll be involving the chat room, and we'll see if we can break some stuff. Well, we've already broken some stuff. We'll see if we can actually fix it on air on purpose. All right, so welcome to Into the Terminal, episode 48. I cannot believe 50 is right around the corner. Today we're talking about troubleshooting disk errors. If you are missing these episodes live, you are missing out on a great time. The chat has exploded with conversation of different troubleshooting tools, different arguments you can use with those troubleshooting tools, and a sarcastic remark about uptime is overrated. DNF update and reboot all the time. I echo that sentiment, but we'll save that for a patching best practices episode. So Scott, welcome. I'm glad to have you live with us today. I feel like I've missed more episodes in the last month or so than I've joined. But you and Nate did an awesome job talking about troubleshooting applications last week. So if you missed that, definitely like and subscribe to grab all of the content. But with that said, Scott, I was trying to do some sysadmin-y type work this morning, and I was trying to write an awesome file, and I ran into an issue where I ran out of space on my device. So I figured this would be an easy place to start diving in and troubleshooting.
Sure. So before we talk about mount awesome file, though, I think we need to roll back and maybe create a file in like your home directory or Etsy or something like that, so we can see our first problem that we've introduced to this box. The awesome file is the second problem we introduced to this box.
That's what I get for using Scott's lab instead of writing my own. But hey.
Okay, so we're trying to create a file. We're told no space left on device. And we know that we can look at how much disk space is available to the machine using what command?
My first inclination would be to use df-h. And I'll add your capital P as well.
And what we see from this is dev SDA2 there, which is our slash file system, is 100% used.
That's never good.
So, no, that's not good. The trick is, though, we have to figure out like what is using that space. So we're going to have to do a little bit of spelunking in the file system to figure out where that disk space is being stored. Now, before we go into spelunking the file system, this machine is using straight file partitions for its disk, which is very common in cloud environments, but less common in data center environments. In data center environments, we'd see something like logical volume managed file systems, and they're getting around this fullness may just be expanding our file system in the logical volume management. And that would resolve the problem for us, at least temporarily. But here, because we're using partitions, like we don't have any other space and no other disks attached to the machine, we need to figure out what's using this space and get rid of it. So we have another tool that tells us how we are using space.
Oh, I missed the prompt. So I'm sorry. So I mentioned that you can use the du command to start digging into an actual file system.
Yeah. And so if we look at the disk usage, and this will pull up the 1K block size, but we need to pass it the / directory, so it goes through a bunch of things. And then, yeah, we're going to redirect the error messages to dev null, so it doesn't pollute our output. And then the other thing we're going to do is we're going to take that resulting output and we're going to sort it using the sort command. -rn says reverse numeric sort. So show me the largest things first. And then less will show it to us one page at a time. All right, let's hit it. So it'll take a while to like crunch through the entire thing. But we can see that var and var log are using the most space on this machine. So why don't we go over to var log and see what's in there. And maybe here we do a ls. Yeah, that'll work. And we have too many files. It scrolled off the screen. All right. So we see right there one really large file, aptly named big file. So that is a lot. If we do an ls-h to see the human readable size, I bet it's like 18 gig or something stupid. Yeah. So if we were to remove this file, that should resolve our 100% used stuff, right? So let's go ahead and do it.
This is very typical of systems administration work. There'd be a big file in var log, and we'd run into issues where I forgot what my point was. Go ahead. I might remember my anecdote later.
All right, so at this point, we've removed the big file, so that should free up 18 gig of space.
But wait.
But wait. It did not. So Eric, just double check. Did we actually delete big file? Is it there?
Yeah, I don't see it.
Yeah, it's gone. Well, it turns out it's not gone. Because to make this even more educational for you, we set up a process to hold that file open. If only there was a command that we had that could show us open files.
You know what? I bet there is. We should ask the guys at the top of the show. They might have one, maybe like lsof.
All right, so what we did was we took that list open files and then Eric piped it to grep. So we're only pulling out the line for that one file we're looking for, right? Instead of having to sort through the sea of data. And looking at this line of data that matches our big file, what we're told is it's still an open file. And it's being held open by a bash process. We're given the process ID. It's owned by root. We're told the device that it's attached to, its size is 18 gigs. And then there's its name, varlog big file. And then in parentheses next to it says deleted. But because a process held that file open, while we removed that file from the directory listing, we haven't actually finished deleting it yet because we didn't want to interrupt the process that was using it. So all that 18 gigs of space is still being used by big file and is still actually stored on the disk. It hasn't been marked for reuse yet. So let's go ahead and kill -9 process 3295. I see Luna and I on the same page.
Yeah, bonus points to Luna there. She already got it.
All right, so before we do that, never mind. So we can see that we've resolved our disk-free problem, and then just to like close the loop, if we do an lsof pipe into grep big file, right, it's not listed in the open files anymore. So as soon as we terminated that process that held it open, then the file system was able to go ahead and mark that 18 gigs of disk space for available for reuse, which then turned that back into free space and resolved our disk full problem. All right, I want to show one more thing, Eric, before we move to our second disk problem today. I see that Steve Cassidy points out that you want to make sure it's not a critical process. Absolutely. But
That's
like,
what I was driving towards was I ran into this so many times as a systems administrator where a critical application had just dumped everything into log files, and the application administrators would just say, just add another disk and expand the file system. No big deal, right? And then 2 weeks later, disk is full again. And so just not cleaning up your applications, not cleaning up files that are in use, not doing log cleanup, just really created an issue that we kept having to readdress.
all right, I see that Shantanu had suggested that we could like blank the file instead of deleting the process. Maybe, but depending on how quickly that file was created of that size, if we blank the file, all we're doing is unblocking the application who had filled it up to start filling it up again. So like, yes, that may be able to buy you some time, but overall, like, you want to address the root cause. All right, but I wanted to show you an example of this in real life. So if we take a look at Etsy log rotate.d, and we should just be able to cat it, Eric.
Now I want to go in there. I want to break stuff.
So what we're looking at is for log rotate, which changes out log files periodically and replaces them with new files. The rsyslog daemon has the inode number of the old log files cached. So if we just move the file away, it continues to write to the original file's data blocks and doesn't shift to the replaced file that log rotate has put there. And so what we see in this this configuration file is that when we rotate these files, there is a post rotate command that is executed that we're going to do a kill-s hup on rsyslog, and then we're going to redirect that to dev null so we don't see anything about it. What that does is it signals the rsyslog daemon that it needs to reread all of its files, including caching or rereading the log files and recaching the inodes for the files assigned. So after we move the files away, the daemon is then hupped, which then gets it to shift writing to the new file that we placed in the directory, so we don't keep writing to the old file that will at some point be deleted or removed from the machine. All right. So this is something that we do, right? It's something that processes do normally on the machine, that they will have a file moved away from them or something changes and they need to be told that. And so something like a service restart or a reload will often resolve that cached inode problem. Speaking of inodes. All right, so we also created this other file system and mounted it into our machine.
And this was the problem that I initiated the call around. You know, Colin Scott had helped us support here.
Right. So if we just try to copy a file or create a file here, we'll get an error message. Right? No space left on the device. But if we look at df, the mount file system says that it's 2% used. Right? So clearly there's plenty of space. But is there, though? So it turns out there's two things that make a file system. One is data blocks for storing file content. But the other thing is inodes. And inodes are a file pointer that tells the directory structure where to find a file. And so if you do a ls-i, what you're seeing here is the inode number that goes with each file that's listed in this directory. So each file has a file pointer that's numeric, and we're told like which one is there. So if we want to look at not just the disk usage or like the data block usage with df, if we use df-i, that will show us our inode usage on the file systems. Yeah, and we see that here we've run out of file pointers. And the way that we got into this situation is I just created a whole bunch of empty files. Eric, if you do an ls-l in the melt directory, right? So all these files exist, but notice that they're 0 blocks in size, right? So creating an empty file uses one of these inodes, uses a file pointer, and they are finite, so they can run out. Now, there are some differences between inodes on different file systems. So for ext formatted file systems, which is what you'll see on older Red Hat Enterprise Linux systems, we use inodes that are predetermined at formatting. So if we do a tune 2fs-l on dmesg3, so this is all the file system information that was put on this file system when we created it. And what we're told is things like the inode blocks per group. So basically, inodes are put around in the file system, distributed. So as we're reading the disk, we can find file blocks close by to the file pointers. We're also told things like the block size for the file system. A lot of this was just automatically determined. But based off of the file system size, the inodes will be created in advance on ext formatted file systems. That's ext2, 3, and 4 formatted file systems. All right, but if we do a XFS, what is it? XFS _info, I think, on devsda2. XFS is the default file system for RHEL 7, 8, and 9. And it tells you the things that the XFS file system was created with. But notice that it doesn't tell me how many inodes were created. It just tells me the inode size. And then it gives me an aggregate size of how much disk space is being used to store inodes. Well, one of the reasons why we used to call XFS the scalable file system is that it would automatically create additional inodes if needed to store files. As long as there were free data blocks that it could convert into inodes, it would do so. So on RHEL 7, 8, and 9, it is much more difficult to get into this situation where you run out of inodes because the XFS file system should create additional inodes as needed based off file activity. All right, MBTDYT asks how to set an inode manually. You don't. They are chosen when you create the file. Each file system has its own inode table and tracks its own inodes. And you just get assigned the next one that's available in the table. So as you get to the end of your inodes, it'll wrap back around to the beginning and look for open ones for files that had been removed from the file system. So these are a finite resource, but generally they don't run out. Like we create a lot of them. But places where you'll run into this is if you store a ton of small files, or you're using things like zero-length files, or you create a ton of directories, because those are very, very small files, which will consume an inode, but not a lot of disk space. And so that's where you can potentially run into problems. But again, with XFS formatted file systems, generally you don't see it. All right, so if we remove all of the files in this mount directory, Eric, cool. And if we do our df-i, Right now we're back down to like a reasonable amount of inodes are available. And this is like a super, super, super small file system, which is why there's only 128 inodes in it. Or was it less than a meg was our file system, Eric?
It was like 980K.
Yeah. So normally the volume of inodes you get is really large. Luna asks about how is this handled in Btrfs? I do not know because Red Hat does not ship Btrfs as part of our selected file systems. You know who will know is, was it Strange Doctor? No.
Eighth Doctor.
Eighth Doctor, thank you. Eighth Doctor does a lot of contribution to the Btrfs file system, and he is intimately aware of how Btrfs pretty much does everything.
Yeah, Eighth Doctor, you can find him out on Matrix, Telegram, just about anywhere. He is an awesome, awesome resource.
All right. So our last problem that we've created for ourselves today is reflected in some messages in varlog messages. So you happen to be just like looking through your messages one day and you see a whole bunch of messages like these. Messages from the kernel. It's telling you about I/O errors. It's giving you specific sectors where the I/O error is. These are extremely scary, and you should be scared of them because these are messages coming from the kernel complaining that it's not able to access certain portions of your disk drive. So the likely culprit is your disk drive is starting to have problems. So your immediate reaction should be, I should back up all of the important data on this drive because it may not be very long for this world. And then your secondary reaction, after you've backed up all the critically important data, is maybe I could try to fix that. So it could just be that that specific sector is bad on the disk. And so you can use tools like FSCK if it's an ext2, 3, or 4 formatted file system, or XFS_repair if it's an XFS file system. And this is going to be a very disk-intensive operation, right? Which is why it's so important that you backed up your data ahead of time, because realize that this disk may be dying and you're about to kick off a really intensive operation on this potentially dying disk that could kill it. So you've already backed up your data, and what you could do is use FSCK or XFS repair to scan the disk. And when it scans the disk, it's going to look for those bad sectors on the disk and keep track of them. So that in the future, when we're doing disk I/O to the disk, if we need to write files, we will simply skip over those already logged bad sectors, right? And then that should resolve this error message. But if the disk is really dying, which it likely is, you will want to replace it. So in that error message, we saw things like what disk device was affected. And that tells you like which disk you should replace. You can also use tools like fdisk to figure out the capacity of the disk so that when you replace it, you're replacing it with a similar size. If you're using something like RAID, where you want all the disks to be the same size. The other thing I would point out, especially if you are using RAID, disks have a mean time to failure. So when they are manufactured, there's an expectation that at some point that disk will die a horrible, horrible death. So if all the disks that are in the system came from the same manufacturer because you bought it all at the same time, and one of them has already failed, then odds are good that the others may also start experiencing problems in the near future, right? So great, you replaced that disk. But what about the next one that came from the same batch that's in the same equipment that may be going bad next? So that's one where, like, if you start to experience that, you need to keep a closer eye on that system because one of your drives reached its mean time to failure. So the others are maybe not far behind. The other thing I would caution you against is if you see error messages like that, don't reboot the system. If your disk is about to die and you reboot the system, what's to say that it keeps spinning after the reboot, right? When you shut it down and the disk stops spinning, it may not spin back up again. So yeah, when you see error messages like that about your disk devices, super scary, should be immediate action of back up the file system data, back up your critical data before you start trying to address and fix it.
Or perform a late night physical to virtual conversion. Not that that's ever happened to me, that we've P2V'd a mission critical server before it dies.
So that's a little bit on like how we use the tools that we talked about in the beginning of the episode to then troubleshoot some disk related problems, right? So it's just like we saw last week when we were talking about troubleshooting services. You need to know what normal operation looks like, right? Normal operation is I have free disk space. I have free inodes. Normal operation is I don't have error messages complaining that my disk is about to die a horrible death. And then some tools to help you out are things like DU, DF, lsof, etc.
So at the top of the show, you mentioned showing kind of how we produce these situations. Do we want to do like a post-credit scene? We can wrap up the episode here, and after the outro, we could jump in and you could talk us through the command line voodoo that you went through to create these scenarios.
Sure.
Okay, awesome. So for those of you that learned a lot, I know that I wish that I had this episode back when I was managing physical servers, because inodes was something that I didn't really have a good concept of until years later, and now most of my servers live and die over like 3 days instead of 3 years. So definitely appreciate folks that suggested doing this episode arc. Really helpful to ourselves and to sysadmins everywhere to have this kind of content. And Scott, just really want to thank you for agreeing to be my co-host for this. Your years of training experience and sysadmin experience, it clearly shows when we start talking about system operations, systems administration at a deeper level. Just shows how much I relied on Google just to survive, just to keep my production systems up and running. But definitely thank you for being my co-host, and really appreciate you being a part of the Into the Terminal family, I suppose.
Yes, as we've expanded to also include Nate Lauder.
Yep. Yeah, he's been doing an awesome job, and even though last time I wasn't here and you all snuck slide decks into the show, but we'll blame Nate. He's not watching this morning, so we'll blame Nate. Anyway, thank you all for joining us live. The chat has been just hopping, so really appreciate y'all joining. Love to see you guys talking about. Really appreciate you guys talking about ideas and sharing troubleshooting tips. So if you've missed the live episode, definitely catch us next week, where we will be talking about troubleshooting network drives, or not network drives. I saw disk errors. Where we're troubleshooting networking next week. Pro tip, it's probably not DNS this time. That was last week, but it could be DNS. So anyway, we are live every Friday. Be sure to tell a friend. And meantime, like and subscribe so you get notified anytime that we go live. And if you're really curious how this episode sausage was made, stick around till after the credits. And we'll talk about that then. And otherwise, thank you all so much for joining us, and we'll see you next time. All right, so I don't know what your meeting schedule looks like, Scott, but I figure I gave you a screen share control, so if you want to walk us through things.
Sure. So a lot of the situations that we set up today are kind of normal to see on systems that get used, right? File system space gets used, inodes get used. They're finite resources and they run out over time. But I wanted to like force that to be the case today. What I did for the file system full is I just used DB. I set the input file to be dev0, which is a never-ending stream of null characters, which take up 8 bits apiece. And I wrote those to an out file of our log file. All right, you want to be really careful when you use DD, though, especially when selecting your in file and out file, because notice it didn't ask me first. It just started writing data. If you typo something and you actually like overwrite another file or overwrite your disk drive, like DD will happily do that for you. Yeah, you want to just be careful with that.
I've never accidentally overwritten a file share with an ISO that was meant to go the other way. Never done that.
Right. While DD is running, you can use kill sig user 1, and it'll actually put out one of these statuses to tell you how much it's copied. If you want a little bit more verbosity, but you have to do that from another terminal since you're actually, you know what? Let's do it this way. I'll put it in the background, and then I'll do a kill sig user 1 on 21069. Right, so when I kill it with the sig user 1 signal, it will tell me like what it's doing as output. Right. So I just let that run until it like filled up the entire file system and aired out. And that's how I created the lack of disk space. For the used inodes, I actually originally tried to do this in the same file system, but because the default file system type for Red Hat Enterprise Linux 7, 8, and 9 is XFS, and XFS will happily convert data blocks to inodes to make more of them for you. It didn't work really well for me. So for that one, we had to create a file system, and I chose to format as an ext4, which does have a finite set of inodes. So we'll wait for a second for our box to provision, and then I'll run through that really quickly. While we're waiting, I can tell you that I tricked you on the failing disk. What I did was I just went out and looked for error messages that indicate that your disk is dying. And then I used a command called logger to stream those messages into log messages. And then we wrapped it with a for loop. So we got a bunch of them together and they'd be easy to find. But I literally just copied and pasted text from like other people's Stack Overflow of like, what does this error mean? And we just put it in our log file. So the disks on these boxes were just fine. We just faked you out with some data in the error log or in the varlog messages.
I think that's a good point, because with a logger command, you can actually put in your own log entries. So if I would use this as a sysadmin, if I wanted to start, I would use the logger command if I was getting ready to start like patch maintenance or something. You could just do a logger and then say, patching maintenance has begun, signed Eric, something like that. Just some custom log entry to just say, I saw this error or I'm starting this process. So you can actually write your own log entries.
Yeah, and I see Shantanu is irritated that I faked him out on that. I mean, the alternative, Shantanu, would be that I open up the disk drive and like get something sharp and like scrape a big, scrape across it and then put it all back together and put it in my machine. That would do similar stuff.
That would be tricky considering these systems run in a Google data center somewhere in the world.
Oh, I'm going to go to Europe and I will go to the data center and I would take that drive out and I'd mess it up on the hypervisor. Nothing could go wrong with that.
I'm sure they'd let you in. It's for educational purposes.
Yeah. I tell them in advance, hey guys, I'm going to take down one of your hypervisors and scrape up its stripe so I can show some stuff on a live stream. Cool? All right. So that one was faked because I just wanted to talk about it. The other thing that we did was we created a file system that ran out of inodes. So I just used fdisk on my disk drive, and I created a new partition. And there's not a lot of space left on this. If we do a print, right, it's like 1 meg of space. So I wrote the changes, part probed the disk, and then did an MKFS MKFS -text4. Right, and so from this output from the MKFS, I was able to find out like how many inodes there were. And I could have then written a 128 iteration for loop to suck up all of the inodes that are in this file system, but instead I mounted it. And then I just wrote a while loop to be very not gentle or sophisticated. Let's see what I do here. All right, let's try this one more time. While true, do touch count file $I, increment I, again, syntax, and then done. All right, so it just like keeps going, but I've already used up all my inodes, so I don't get any space left, right? And there's the files. So if I do a df -I, right, I 100% used it. So yeah, that's how I created those problems. The other problem that we did was, we made the big file, but then we couldn't delete it because a process had to open.
Oh yeah.
So that one I also kind of tricked you on. Let me create that big file one more time.
Yeah, Luna asked if urandom would have worked too. So yes, using dev urandom would have just put a bunch of randomized characters into big file.
Yeah, but unlike dev0, urandom is numbers that are randomly generated. So dev0 just is very low effort for the computer to pull a null character and stick it in big file. If you pull from dev urandom, it actually has to generate a random number to then put it in big file. So what you'll see if you used urandom is that you will likely see an increase in CPU utilization because you're generating those random numbers to then put them in this file. Whereas dev0 is just a null character. All right. So to make it so that we could delete it, but not really delete it, I created a tmux session, and we did a exec 5 double greater than on our file. All right. So what this does is it executes a process, and then 5 double greater than basically opens the referenced file for appending. 5 single greater than would open it for overwriting. And that process is running. We've logged, or it's attached to the shell, I should say. And so if we come out of our tmux session, let's put, and I didn't install lsof. So I won't be able to show you that. But that's how I created that situation where we deleted the file from the file system, but that process running in my tmux was still running, and that's why a bash shell held it open. And when Eric killed it with the -9, that killed the tmux session and the shell, which then made the file not open anymore. So that's how we resolved it.
Awesome. I feel like you and I should now be in an Avengers movie because we have a post-credit scene now.
Only was bloopers.
I tried that in a podcast. I don't think anybody ever heard it. So that's kind of all the questions, and definitely a great episode, and really appreciate you kind of taking some extra time to talk about how the sausage was made. Some of it's a little bit of on-screen tomfoolery, but the rest of it is real-world situations. I can distinctly remember deleting a file and it not being deleted. So rebooting the server, and that fixed it, which was kind of, rocket launcher to a fly approach of fixing that issue. But when you're just a dumb Linux systems administrator and you just started out, yeah, I think you lost a fan in Shantanu.
I'll be back. He likes it when I'm up to hijinks. Honestly, like the reboot of the server, like that fixed it because you killed the process that was holding the file open, which, there you go. Problem solved.
Right. Probably didn't need to kill the other 1,000 some odd processes that were running, but, hey, I fixed it.
Fair enough. Fair enough.
All right, folks. Thank you so much for sticking around. Really appreciate it. And we will see you next week.